most demanding requirements for power or energy transients. And so you went through the list of residential, commercial, industrial, and transportation sectors. And you might have thought residential and commercial sectors both have diurnal needs, so from day to night, and their seasonal needs as you move from, let's say, winter to summer. So that provides demands for heating, ventilation, and air conditioning. And then you might have moved on to the manufacturing sector, where you say, well, the manufacturing demands might change again, both by day, different shifts, things like that. But I challenge you to look at the transportation sector and consider the issues associated with energy and power demand and transportation. For example, let's say you're driving down the highway, semi-tractor truck pulls out in front of you, you need to get out of the way. You push your foot down on the pedal, and you have an expectation that that car will deliver power in a fraction of a second. Similarly, if you're on a jet airliner and you're getting ready to take off, that jet airplane needs to be able to provide thrust in a matter of seconds, and it's a huge amount of energy. So the transportation sector not only requires, very fast demand of energy, but it also has to operate over a really broad range of speeds. And we have the additional constraint that the transportation sector has to carry its energy with it. The energy carrier has to be on board because the device is moving. So I'd argue the transportation sector is actually the most difficult to make changes because the demands for performance are so high. Okay. So now we've kind of discussed what are our drivers. We have supply and demand. We know there's population growth. We know that we have a global community and we have different needs around the world. Now what we need are the tools for us to be able to analyze these systems. And that's where thermodynamics is the tool set that we need to be able to understand what we can accomplish, what we can't accomplish, what are the limits, what are the ideal behaviors. So thermodynamics is the study of energy and the interaction of energy with matter. So we want to consider energy systems, how we can obtain energy, how we can transfer energy from one type of energy to another, and how we can apply energy to specific systems and processes. So now what I want to do is give you some examples of those different types of energy transfer that we're going to consider in this class. So if we start with transforming energy, an excellent example that we're all familiar with is the classic pushing a ball up a hill. So we know that as we push the ball up the hill, we increase the potential energy of the ball, and as we release the ball, that potential energy is converted into kinetic energy. So we can see the conversion very obviously from potential to kinetic energy. So that's a good example of transforming energy. For example, another good example that's relevant to the stationary power sector is a dam. So we know if we have a hydraulic system that the water is elevated before it comes into the dam, and then that water passes through turbines, which are used to spin shafts to generate power, and then they exit the dam at a lower elevation. So we know there's a conversion of kinetic energy of the water as it's moving through the river, and potential energy because it's at a high height prior to going through the dam, into mechanical energy, which is the spinning of the shaft associated with the turbines. So thermodynamics helps us quantify the transfer of energy from one type of energy, one category of energy, to another. Additionally, we want to be able to obtain energy, and that's probably the best example is actually extracting energy, is the example of the dam that we just considered. So, for example, we want to convert that kinetic and potential energy to electrical energy, ultimately, to mechanical work, which we will define in detail to electrical as we move further along in the course. So we'll transform, we'll obtain, we'll want to generate and apply energy in a number of different systems. And so there we can think about, well, let's generate power, for example, to power a battery, or excuse me, to use a battery to power a laptop computer, for example. So how do we apply that energy transfer? Really involves three kind of classic energy transfer mechanisms, and we'll discuss those again in detail in this class. So these would be examples where sometimes the actual example is to generate power. So that would be, charging a battery, for example. And sometimes electrical power isn't the ultimate goal. So we might be generating, let's say, again, our example of a jet engine is actually the goal is to generate thrust, not to generate power in the conventional electrical energy sense, but it's to generate the thrust that's necessary to get the jet off the ground. So again, thermodynamics covers all of these systems, whether or not your key here is to generate stationary power or propulsion, or whether or not it might be almost a parasitic loss or a supporting need for whatever your application is. As long as there's energy transfer involved, we have the tools within thermodynamics to analyze the system. Now, heat transfer is a classic example of where we may not be making a power plant or designing a new jet engine, but heat transfer could be very relevant to our system. So here, heat transfer is very specifically how energy is transferred when there's a temperature difference. So anytime you have two systems that are at two different temperatures, there's energy transfer due to heat transfer. So anytime a temperature difference So heat transfer is a form of energy transfer. So let's just take kind of the classic academic example of we have two bricks, and one is a mass of an amount mass A, and the other has an amount mass B, and they could be the same amount of material or different, it doesn't matter. And we have two temperatures where one is greater than the other. So let's say the temperature of material B is greater than the temperature of material A, and because we want to make our life easier, we'll just assume that the mass of the two systems are the same. If we bring those two bricks together, we know because there's a temperature difference that there's going to be heat transfer between the two systems. Intuitively, we know that the heat transfer will be from the high temperature material to the cold temperature material. So we know also that the final state, when the system comes into equilibrium, which it will do, it will reach a thermodynamic equilibrium, that the temperature will be somewhere between the two temperatures of A and B. So if we bring them together, and at equilibrium, the temperature of A will equal the temperature of B. And this will be a temperature, so this will be, we'll call this the temperatures all at the initial state or state 1, and the temperatures at state 2 or the final state will be equal. So again, if we see any temperature difference between two systems, we know that there'll be heat transfer. So that's a very easy energy transfer process for us to identify. Now, there are three types of heat transfer, and there are physics associated with each of those three heat transfer mechanisms. And those three types of heat transfer are conduction, convection, and radiation. And we won't cover the details of the physics of these different mechanisms in this class. We'll just identify whether or not there is heat transfer present, and we'll quantify them in a general form, but we won't quantify them from initial principles based on these conduction and convection and radiation principles. So that's heat transfer. Next, we'll talk about fluid mechanics. So fluid mechanics is the motion of the fluids, which include, when I say a fluid, we don't just mean liquids. A lot of times people will think, oh, that's a liquid, but we mean liquids and gases are both in the category of fluids. And the transformation of energy between mechanical and thermal forms of energy. So fluid mechanics is the motion of the fluids. Thermodynamics doesn't consider the details of the fluid mechanics. We only consider the high-level picture associated with energy transfer due to the motion and the processes of fluids. So now we need to go through some definitions. It's going to take us a little while to go and develop the tools and the vocabulary so we can actually go through and do quantitative analysis. So let's start with defining a system. So a system is the object that we're going to study, that's the object under consideration. And closed systems are systems where the mass is fixed. The mass does not vary in the time that we're considering it. So like a brick, if we're considering maybe my brick cooling or my two bricks coming into contact with each other and equilibrating, that's going to be a closed system where there is no mass crossing the system boundaries. An open system is one where mass can cross the system boundaries. So a great example for an open system would be like your garden hose. So let's say you're directing water through a fire hose or a garden hose. We know that the water enters one end of the hose and then it exits the other end of the hose. So that would be an open system. So what I want you to think about right now is let's consider a system that's maybe your coffee mug. If you want to consider the coffee inside your mug, maybe we're going to do a heat transfer analysis to see how long it takes for my coffee to cool. Would that system be best described as an open system or a closed system? So I want you to think about that. And then the other example I want you to consider is the CPU, or the power, the brain, if you will, in your computer. Is that best described as a control mass or a control volume, as an open or closed system? And that's the best way to consider these two examples.